Experiment 5 is about acid-base titration, percentage acetic acid in vinegar. The objectives for this experiment is to standardize a base solution NaOH using the primary standard potassium hydrogen phthalate, or KHP. And then after you do the standardization, you're going to analyze a sample of the vinegar, calculate its percentage acetic acid it contains, and compare the result to that on the printed on the label. In chapter 4, we have defined acids and bases, and we're just going to repeat that definition here. So acid has been defined several times, and the first definition of acid is done by Svante Arrhenius, when he defined acid as any substance that gives H+ when dissolved in water. Then Bronsted-Lowry also defined acid as proton donor. Base, on the other hand, is defined by Arrhenius as any substance that gives hydroxide when dissolved in water. And this definition is really so narrow because you're limiting bases to all those what we call hydroxide containing compound. So ammonia cannot be defined as base. Now Bronsted-Lowry definition widened the scope of the bases when they define it as proton acceptor. Now titration is what we call a volumetric method. Okay, so when you say volumetric method, we look at the volume. So volumetric analysis or titration, what you have there is you react a substance of a known concentration with something that has a known concentration. So for instance, in the setup of the titration, this is what you have. You have the burette that contains the titrant, okay? And then you have the receiving vessel that contains the analyte. So in the titration, you're trying to determine the concentration of the analyte based on the amount of volume and concentration that the burette has. So during titration, you have this so-called equivalence point wherein there is a stoichiometric relationship that you can find between the titrant and the analyte. So usually they are in terms of moles. They can be 1:1 mole ratio or 1:2 mole ratio. Now, one type of titration that you're going to do in this experiment is called standardization. So this is the process of determining the exact concentration of a solution. So there is a problem when you prepare NaOH solution. Sodium hydroxide is hygroscopic. That means it has an ability to absorb moisture in the surroundings or in the environment. So whenever you weigh it, it's the exact mass of NaOH is lower than the one that you recorded. So for you to determine what's the exact mass, you have to standardize it. You have to titrate it with a primary standard. And the one that you use here is the KHP, the potassium hydrogen phthalate. And the way that you're going to do the experiment in part 1, you're going to standardize your NaOH with KHP. So the way that you're going to have there, so you get the mass of the KHP over its molar mass, so that will give you the moles, and on the other side you have the concentration, mass over not mass, it's moles over liters, and you have what we call the volume that you use in liters as the equivalence point. So you know this mass, you know the molar mass, you know the volume based on the equivalence point, so you should be able to determine the exact concentration of your NaOH. And once you know that, in part 2, you're going to use the same NaOH solution, this time to titrate with acetic acid. For this experiment, the first thing that you're going to do is the standardization of the sodium hydroxide solution. Now to do this, you're going to weigh about 0.5 to 0.7 gram of the standard potassium hydrogen phthalate, or known as KHP. Okay, and you're going to place this in a 250 ml beaker and then add 50 ml of water. You're going to use a small magnetic bar in the beaker and put it in a magnetic stirrer and stir it until all the KHP solid has dissolved, and then you add 3 drops of phenolphthalein that serves as your indicator. Okay, now you're going to put around 200 ml of NaOH in another beaker, 250 ml beaker, and then this will be the source of your NaOH that you place in the burette. Now, before you put the NaOH in the burette, maybe run some small amount of your burette with the NaOH to wash it or rinse it, and then fill it up. Okay, open the stopcock, let some NaOH flow, okay, so that you don't have any trapped airs. And then you're going to use here a setup known as a Lagerfeld Bernier. So you have a pH electrode that you place in the beaker that contains the KHP solution, and this pH electrode is connected to a computer. We're not going to use the drop counter, so we're just going to use fixed amount of volume, let's say 1 ml 1 ml, and then record the pH manually. So once you have this set up, you start titration by adding NaOH to the sample. You record the pH with the corresponding volume of the NaOH solution that is added. So you will see a sudden increase in the pH once you reach the so-called equivalence point, but just go over that so you can have a plot. Now, in the second part of the experiment, which is the percent acetic acid in the vinegar, what you're going to do is you weigh a clean dry 250 ml beaker and then add about 5 ml of the vinegar and weigh it again. So the difference in the weight there is that of the vinegar. And then you're going to add 50 ml of distilled water, okay, and 3 drops of the indicator phenolphthalein, and then you place it in the setup where you have the magnetic stirrer. Place the pH electrode in the beaker. So you're going to fill up your burette with the NaOH, whose molarities you know now based on the previous part of the experiment. So you're going to titrate it. You record the pH with the corresponding volume of the NaOH added, and you will see an increase in pH at some point, a sudden increase in the pH at some point. You just let go over the titration, okay, and then you should be able to get the amount of the acid in your vinegar sample. So both part A and part B will be done twice. So you're going to repeat again both parts of the experiment. Now, since you are using a Lagerfeld in this experiment, okay, when you're doing the titration, you will have a plot like this one. Okay, so in this case, you usually obtain the equivalence point. So the equivalence point would be here. Now the software can process your data, and if you get the so-called first derivative, this is how the first derivative look like. And as you could see, the first derivative agree, okay, with the plot that you obtain in terms of the volume at equivalence point. So the volume at equivalence point, that's corresponds to the same moles of the acetic acid with your sodium hydroxide. The data given to you would look like this. You have the weight of the KHP sample, and the volume of the NaOH at the equivalence point for the standardization of NaOH. So how are we going to do the calculation? So if you read the manual, there's a portion of the calculation there, and I'm going to show it this how you're going to do it here. So you have there 0.5342 grams, and you're going to divide it with 204.22 grams per mole. Okay, so this represents the KHP, and if you're going to do the operation here, 0.5342 grams divided by 204.22, you're going to get a value which you're going to divide with the volume that you have here, and we can simplify this as 26.15 ml divided by 1000 ml per liter. Okay, so if you're going to do that, you're going to get a corresponding value that is around 0.100 moles per liter, or 0.100 molar. Okay, so what you can do with that one is whatever value that you have here, you add it with the value here, divide by 2 to give you the average molarity. Now you have to do that because you're going to use this value in the next calculation. The next data set given to you would look like this. So if you have this, all you need to do is to fill up the blank. So for instance, the blank that you have here can be obtained by just subtracting this number with this number. So if we're going to do it, 94.28 minus 89.05, that will give you around 5.23 grams. Okay, and then you're going to use the volume of NaOH here to get the number of moles of your NaOH, and indirectly the number of moles of your vinegar. Okay, so remember what you did earlier, you end up with 0.100 moles per liter. So what you're going to do, you can multiply it with here, with this value, 43.45 ml per liter, or 1000 divided by 1000 ml per liter, and then you're going to multiply this with 60 grams per mole. So this is to get the mass of the acetic acid. So if you have that 0.1000 times 43.45 divided by 1000, and then times 60, so you end up around 0.2607 grams. So this represents the amount of the acetic acid. Now to get, okay, the percent of acetic acid in your sample, you're going to use this value, 0.2607 grams divided by 5.23 grams, because that's the mass of the vinegar that you have, and then you multiply it with 100. So you have here 0.2607 divided by 5.23. So you multiply it with 100, so you end up with 4.98%. So you're going to put this value here. So whatever you get here, you add it with the value that you have here and divide it by 2 to get the average. Okay, so in the experiment that you're going to in the lab report that you're going to submit, you're going to fill up all the data, show some sample calculations, and answer the question. Okay.